Okay, so the next thing I want to address real quick is the notion of drawing electron dot structures of compounds containing only hydrogen and second row elements, so stuff like carbon, nitrogen, and oxygen. This is important because most of organic chemistry, if you've come across that term or if you'll actually be taking that class, revolves around compounds that largely consist of carbon, hydrogen, and other elements, most of which are in row 2. Now, to do this, at least the examples you'll be given in this class, really what you want to do is just kind of hone in on the fact that for second row elements as well as hydrogen, there's a certain number of bonds that you expect each atom to form and a certain number of lone pairs to have. So if you go back to that chart where, for instance, it shows that carbon has 4 valence electrons and is expected to form 4 bonds, nitrogen has 5 valence electrons and is expected to form 3 bonds, and so on. The vast majority of compounds that contain carbon, hydrogen, and then other second row elements are basically going to be dictated by that. Now, if you get to larger chemical formulas than, say, the one you see here, ethane C2H6, if we get to something with a lot more carbons and hydrogens, there's actually not a way for you to convert the formula into one and only one correct Lewis structure. So your examples are going to be limited to simple ones, or at least relatively simple ones like ethane here, where given a formula, you can apply the expected number of bonds to arrive at an unambiguous structure. So if you look at the Lewis structure for ethane, especially there on the right, you can see both carbons have 4 total bonds around them, and each hydrogen has 1 bond, and there aren't any lone pairs on any of the atoms, and both of those things are consistent with the way we would expect those to behave based on the table of number of bonds formed on a previous slide. And we'll actually look at an example of this later on. For now, what we're going to go ahead and do is move on to the notion of resonance structures. So for this, we're actually just going to look at an example that seemingly starts the same way as all the other examples that I showed you where we went over how to draw different Lewis structures from formulas. So for this example, we're going to use ozone, which is O3. Regular oxygen is O2. O3 ozone, it's the same stuff that's in the ozone layer, if you've heard of that before. It's also a pollutant if it's closer to ground level, but it plays an important role in the Earth's atmosphere at much higher levels of the atmosphere. Anyway, this consists of 3 oxygen atoms bonded together, so let's see if we can draw a Lewis structure for this. As always, we're going to start by figuring out how many valence electrons we have, so that should be each oxygen has 6 valence electrons, there's 3 oxygens, so that should be a total of 18. Step 2 is to connect the atoms. In terms of what to choose for the central atom, we really only have one option, it's oxygen, so we'll just put one oxygen in the middle and attach the other 2 to that central oxygen. So we end up with O, single bond, O, single bond, O. That used up 2 pairs, or 4 electrons, so we have 14 left. Step 3 asks us to use as many as we can to fill out the octets of the outside atoms, so those would be the left and right oxygens there, I guess. So if you put 3 lone pairs, or 6 electrons around each, combined with the single bonds that we already had, then both of those oxygens on the outside will have 8 electrons each. And if you count up everything, we should still have 2 electrons left after step 3. And so we're going to put those on the central oxygen, since that's the only place to put them. And so we'll have 1 lone pair on our middle oxygen. Now, here's where things become interesting and where the notion of resonance comes in. If after step 4 we look at our oxygen here in the center, we have a lone pair and then 2 single bonds. So we have 3 pairs of electrons around this, meaning we have 6 valence electrons around our central oxygen. Now, obviously, if we're following the octet rule, we'd like to have 8 electrons. So we don't have enough electrons, which means as with previous examples, what we're going to need to do is take a lone pair from an outside atom and use it to form a bond instead of a lone pair. So what we can do is, you can see we have oxygen both on the left and on the right that have some lone pairs. We could use one of those to form a double bond. And so you can see with the rightmost oxygen, we've taken one of these lone pairs and dropped it in between our two atoms so that we now have a double bond here at step 5, which gives our central oxygen, this guy right here, 8 electrons around it. We have 4 pairs, 1 lone pair and 3 bonding pairs. And each of these outside oxygens still each have 8 electrons around them. This lone pair is still accessible to the oxygen on the left because it's sharing it with the inside oxygen. Now, you may ask, and this question is basically a giveaway that we're dealing with a situation where we need to invoke resonance. Why did we use the oxygen on the left? Why couldn't we use the one on the right? And the real answer is the true Lewis structure of this molecule is actually some hybrid in between using the oxygen here labeled in red and the oxygen labeled in green. So at step 4, we had what you see up there at the top of the screen, and we could use a lone pair from the red oxygen, which is what we did in the previous slide, or the green oxygen. And if you use a lone pair from the red oxygen, you get the resonance form shown here on the left. And if we use not a lone pair from the red oxygen to form a double bond, but one from the green oxygen instead, then we're going to end up with this resonance form over here. Now, the reason why there's 2 Lewis structures that apply to this molecule, which are what these 2 resonance forms, as they're called, are, is because the true bonding situation can't be completely adequately represented by a single Lewis structure. And whenever you have a situation like this, especially where you need to kind of decide where to take electrons from which of adjacent atoms to complete the octet of the central atom in step 5, that's a situation where you're going to have resonance forms of your molecule. And so the true electronic structure of ozone is some sort of average of the 2 individual structures that you see. And for any resonance form or set of resonance forms, what you do is you just write out all the different resonance forms and you put these double-headed arrows in between the resonance forms to indicate that they're both resonance forms. This is not a reaction arrow. Notice that it points in both ways. This is just showing that the 2 Lewis dot structures here are both representations of the correct electronic structure of, in this case, ozone. Now, one way we have to evaluate resonance forms is by calculating formal charges for each of the atoms in any Lewis structure. And in fact, you can calculate formal charges for all the atoms in any structure. It doesn't have to be one with Lewis structures, but we're going to use ozone here as an example. Now, formal charge has this formula that you see on the screen right now, and you might be wondering, why are we going to use this arbitrary formula? And it turns out that if we apply this formula, we're actually going to end up with a number that we can assign to each atom in a Lewis structure. And the value, specifically the interpretation of that value, can tell us how good of a job any Lewis structure does of representing that given Lewis structure. So you can see the formula there, which is the number of valence electrons in a free atom, which, since we're dealing with ozone, these are all oxygen atoms. That number will always be 6, since a neutral oxygen atom has 6 valence electrons. And from that, you're going to subtract the number of bonding electrons times 1/2. You could also think of this as subtracting the number of bonding pairs. And then we're also going to subtract from that the number of non-bonding electrons, so the number of electrons in lone pairs, and we're not multiplying that value by 1/2. And the value that we get shows us in a Lewis structure what the electron density around each atom in the Lewis structure should be. So the more positive the value of the formal charge, basically that corresponds to a lower electron density. And if we have a more negative formal charge, then that corresponds to a higher electron density. So you can see here at the bottom of the screen that oops, sorry about that. We'll get to that in a second. For each of the three oxygens that you see here on the screen, we can calculate the formal charges just by plugging in the relevant values. So for the leftmost oxygen, assuming that we have this structure where the double bond is between the left and center oxygen, this oxygen on the left has a formal charge of 0. This oxygen here in the center has a formal charge of +1. And this oxygen here on the right has a formal charge of -1. Now, what this means is that the oxygen in the center is relatively electron poor compared to the other two oxygens, and in this resonance form, the oxygen there on the right is relatively more electron rich. Remember, electrons are negative, so a negative formal charge implies a more electron rich atom. Now, in terms of interpreting formal charges and what they say about resonance forms, we can look at the formal charges on atoms in a Lewis structure and use that to interpret how good a resonance form is. Now, for pretty much any atom, the best possible formal charge in any Lewis structure is going to be 0, because we want to have it overall electrically neutral. Now, to make this Lewis structure that we have here, we had to obey the octet rule, which is more important than anything to do with formal charges. And you can see that we ended up with an oxygen with a +1 formal charge in the middle and a -1 formal charge on the right. Now, when we look at some other examples with resonance, we'll actually go through and do one here in a few minutes. If you have negative formal charges, you want those to end up on more electronegative atoms, and vice versa. So when all three of these atoms are oxygen, I guess it doesn't really matter all that much, but when we look at an example where we have two different types of atoms in a resonance form, which is something we'll do on a later slide, then I'll show you how we can use formal charges to actually determine which one of the resonance forms that we draw is the best resonance form. So now that we've gone over all of this, including resonance and formal charges, let's go ahead and look at a few examples for illustrative purposes. So just like in class, what I'm going to do is encourage you to pause the video and try to draw each of these on your own, and then I will walk you through how to determine the answer for the correct Lewis structure for each of these examples. So this first example is going to be to draw the Lewis structure of the compound with formula C2H5Cl. And for this, notice that most of the atoms here are carbon and hydrogen. When you attempt this problem, just know that you can apply those rules where carbon should normally form 4 bonds, hydrogen should form 1, and in this case, chlorine, like most halogens, will form just a single bond. So see if you can come up with what the right answer to that is. So go ahead and pause the video, and I'll come back in a second. Okay, so hopefully you've attempted this problem on your own. Let's go ahead and actually draw this. So the first step of drawing any Lewis structure, of course, is going to be to determine how many valence electrons we have. So step 1. And we have 2 carbons, so 2 times the number of valence electrons in a carbon atom, which is going to be 4, plus we have 5 hydrogens, so 5 times the number of valence electrons in a hydrogen atom, which is 1. And then to that, we're going to add the number of valence electrons from 1 chlorine atom, which, since it's a halogen, will be 7. So 2 times 4 is 8, 5 times 1 is 5, and 1 times 7 is 7. So altogether, this should give us, let's see, 8 and 5 is 13, plus 7 is 20 electrons. And specifically 20 valence electrons, but those are the only ones that we want to incorporate into our Lewis structure. Now, remember carbon is pretty much always the best choice for a central atom, if it is in the molecule at all. And in fact, this formula might remind you of the example of ethane from a few slides ago, which was C2H6. And if you remember back to that molecule, we had a carbon-carbon single bond, and we had some hydrogens, 3 hydrogens attached to each molecule. Or I'm sorry, each carbon. So 3 hydrogens on that carbon, and if this was ethane, we'd have 3 hydrogens on the rightmost carbon too, but notice we only have 5 hydrogens and 1 chlorine here. So we're going to replace one of these carbon-hydrogen single bonds with a carbon-chlorine single bond. And so something like this is going to be the best structure for C2H5Cl. Now, putting this skeleton together is essentially what step 2 is. So if we count how many single bonds we have 1, 2, 3, 4, 5, 6, 7. So there aren't any lone pairs on this molecule yet, but we have 7 bonding pairs of electrons, which means that we've used up 14 of our 20 electrons that we started with. And so we have 6 remaining after that step. Now, step 3 is to assign those electrons to outside atoms to complete their octet. And let me go ahead and erase those dots just so they don't look like electrons. Alright, there we go. Now, we have, as outside atoms, we have hydrogens and we have chlorine. Now, hydrogen shouldn't ever have any lone pairs on it. It should only have one single bond to something else, and that's it. Our chlorine, though, wants to have a complete octet, and it currently only has access to one single bond here. So this thing needs 6 more electrons, and as it turns out, that's exactly how many we have left to place in this molecule. So we can add 3 lone pairs to this to account for those 6 electrons. So that uses up all of the remaining electrons. And so we have this Lewis structure here. 3 lone pairs around our chlorine. And so since we're out of electrons, there is nothing to do at step 4. We can't assign any lone pairs to any carbons or anything. And then step 5 asks us to examine the central atom, or atoms, which would be the carbon atoms, and to determine if they have complete octets. So each of these carbons is surrounded by 4 bonding pairs of electrons. So in the case of the carbon on the left, that is 3 carbon-hydrogen bonds and 1 carbon-carbon bond. And in the case of the carbon on the right, that's going to be, again, this carbon-carbon bond, and then 2 carbon-hydrogen bonds and a carbon-chlorine bond. So each of those has access to exactly 8 valence electrons, and so we are basically, we've accounted correctly for all of the electrons that should be around those carbons. And so the structure you see here is the correct one for C2H5Cl. Now, a word of clarification on where this chlorine went. You might be looking at the structure and wondering, say if we compare this to ethane, let me go ahead and scroll back a few slides to that. You might be wondering, why did we replace this particular hydrogen in the structure with a chlorine? And the answer is it doesn't matter which of the hydrogens were you essentially replaced with a chlorine here, because they're all basically identical. So that might seem a little bit strange at this point, but just know, for instance, that what you see here would be exactly the same as, say, something like this, where you could have a chlorine on some other part of that same carbon, or indeed you could have a chlorine atom on the other carbon atom as well. So something like this. So any of those 6 hydrogens can equally be substituted with a chlorine and you'll get the right answer. And whenever you're given a chemical formula like this in any of these examples that you have to try on your own, the answer you get will be unambiguous, so you won't end up with a situation where you need to pick one of several possible forms. So that's that example. Let's go ahead and look at this next one, BF3. This is boron trifluoride. Now, I want to go over this example for one sort of violation of the octet rule that we haven't really covered yet, which specifically involves boron, and I guess other elements in the same family, so like aluminum and gallium, but boron is really the main culprit here. So what we're going to do is we're just going to start drawing this like normal. Boron has 3 valence electrons, so there's just one boron, so we have 3 valence electrons from that. And then our fluorines each have 7 valence electrons, and there are 3 of those. So we need 3 times 7 for that. 3 times 7 is 21. Add 3 more to that, we get 24 electrons. So that's the number of electrons we have to place in this Lewis structure. So let's go ahead and move on to the next step. Now, fluorine shouldn't ever really be the central atom in any of these molecules we draw. It's so electronegative and it only ever forms one single bond to anything else. So we're going to put boron in the middle of this molecule. And we'll attach the 3 fluorines to that. And so our 3 fluorines will be on the outside of this molecule. So we have 3 single bonds there. So we used up 6 electrons, meaning we now have 18 electrons left. Now, the next step, step 3, is to assign these electrons to outside atoms to complete their octet, so our fluorine atoms. Each of these fluorines only has 1 bonding pair of electrons available to it, so they each need 3 lone pairs or 6 electrons. And it just so happens that if we do that 3 times, so 3 times 6 is 18, that will completely use up all of our remaining electrons. So we won't have any electrons to place down in step 4 of this process. So after step 3 and step 4, we end up with the structure you see there. A boron in the middle, 3 single bonds to fluorines, each of which has 3 lone pairs of electrons around it. Now here's where things are a little bit unique with boron. So with a normal molecule, what you would do is you check on the center atom, which is boron, and you count up the number of electrons around that, and you try to determine if we need to form any double or triple bonds to complete its octet. And if we look at boron right now, it's got 3 single bonds around it. So that should be 6 total electrons. And as the name octet rule implies, most atoms should want to have 8 electrons around them. Now, boron is an exception to this because it actually starts off with so few valence electrons, just 3 of them, that if this was maybe some other compound that didn't have boron in the middle, you might think we need to take a lone pair from one of our fluorines, let's say the one in the upper right there, and turn it into a double bond like this. So we'd have 2 lone pairs left there, and then two single bonded fluorines with 3 lone pairs each. So that is what you would do for a lot of compounds, but if you have 6 electrons around boron, that's actually okay. So in particular, with this example, this is not the right answer. And to go over why exactly that isn't the right answer, we can assign formal charges to these, and we'll go over the details of how to calculate that in a minute when we look at a problem with some resonance forms. But suffice to say, right now, I'm just going to show you the values. This boron has a formal charge of -1. 2 of our fluorines have a formal charge of 0. That part's okay. 0, 0. And this fluorine right here actually has a formal charge of +1. Now, one of the things about formal charges is you don't want positive formal charges to end up on electronegative atoms. So fluorine having a positive formal charge is really a big no-no, especially when our boron here has a -1 formal charge. So even though this gives us an octet, this is not going to be the right answer for this molecule. And this thing, which actually doesn't have a full octet around boron, is going to be the right answer. And really, again, this is something that only applies to boron. Most other atoms aren't okay with having 6 electrons around them. Okay, so for our next example, let's look at drawing the structure of phosphoric acid. And I'll give you a minute to try this on your own. So go ahead and pause the video. I'll come back in a couple of seconds and we'll go over what the right answer should be here. Okay, so hopefully you've tried this example on your own. We have 3 hydrogens, so we're going to have 1 valence electron from each of the 3 hydrogens. We have 1 phosphorus, and phosphorus has 5 valence electrons. It's directly beneath nitrogen. And then we have 4 oxygens. So 4 times 6, each of those oxygens. And so if we add all that together, we get 3 plus 5 is 8, plus 24 is going to be 32 electrons. So with that in hand, let's go ahead and start putting this molecule together. So in terms of the central atom, the best answer here is phosphorus. Now, it's never going to be hydrogen, so we can eliminate that possibility pretty much right away. So between phosphorus and oxygen, phosphorus tends to form more bonds than oxygen. It's directly beneath nitrogen, so it tends to form at least 3 bonds, and actually there's many examples, because it's in row 3, of it forming more than just 3 bonds. Oxygen normally only forms 2. And in addition to that, phosphorus is both to the left and below oxygen in the periodic table, so it's less electronegative. So all lines of evidence say we should probably have this phosphorus in the middle and attach our oxygens to the outside. Now you may notice that I put all 4 oxygens around the phosphorus and none of the hydrogens. And this is because hydrogen is really kind of a dead end in terms of a molecule, since it can only have 1 single bond. So we have 4 oxygens around our phosphorus, and we can start attaching hydrogens. Now, the hydrogens, of course, are going to go on our oxygen here. Now, the first hydrogen you can just assign to any one of these 4 oxygens equally well. Where does the next hydrogen go? And to help you figure this out, it's helpful to remember that oxygen should normally form 2 bonds and have 2 lone pairs. So specifically, oxygen doesn't usually have 3 bonds around it, usually just 2. And notice that when we put our oxygen, attached it to a hydrogen as well as the phosphorus that it was initially attached to, that already has 2 bonds. So we probably want to attach these hydrogens to 3 separate oxygens rather than attach them to the same oxygen, or like have one oxygen with 1 hydrogen and another with 2, for instance. Each of those 3 hydrogens should be attached to an oxygen, and just like the example from a couple of slides ago, you can attach those hydrogens to any one of the oxygens. So for instance, you could have attached one of the hydrogens to the top oxygen instead of one of the other positions. That's totally fine. So this is actually the skeleton of our molecule, and we actually put in a fair number of single bonds doing this. So the phosphorus, we have 4 phosphorus-oxygen single bonds, and then 3 oxygen-hydrogen single bonds, so that's 4 and 3 is 7 total bonds. So 14 electrons got used up because each of those is a pair. So that means we have 32 minus 14, which is going to be 18 electrons remaining at this stage. So the next step is to complete the octet of our outside atoms. The hydrogens, of course, should just have one single bond and nothing else, but our oxygens currently only have 1 or 2 bonds around each of them. So what we need to do is assign these 18 electrons to our oxygens. So remember, we're completing their octets. We're not necessarily always assigning 3 electrons to each. So for instance, this oxygen on the left doesn't have 1 bond associated with it, it has 2. So we only need to put 2 lone pairs of electrons there. So we used up 4 there. We're going to use 4 on this bottom oxygen, and 4 more on this right oxygen. So let's see, that's 4 and 4 is 8, plus 4 more is 12. We have 6 more electrons left, and that happens to be the exact amount we need to complete the octet of this top oxygen there. So that's going to have 3 lone pairs. And so that uses up all of our electrons. We don't have any left. So in step 4, there's nothing to assign to the central phosphorus atom. Now step 5 asks us to examine the central atom, which again is phosphorus, determine if we have a complete octet. And it turns out that we do have a complete octet. This phosphorus is surrounded by 4 oxygens. There's 4 single bonds there, so that's 8 electrons around this guy. So there's nothing to do here in terms of forming any double or triple bonds. So this is your final structure for phosphoric acid. And again, the only difference here is which of the oxygens has 3 lone pairs and no hydrogens versus 2 lone pairs and 1 hydrogen. And you can put those at any 3 positions you want to. It doesn't have to look exactly the way that I have it there. All right, so what we'll do is, for this last example in Chapter 7, we're going to look at an example where we need to invoke resonance. So for this, it asks us to draw the resonance structure of nitrous oxide, which is used as an anesthetic and also in whipped cream as a propellant. And this consists of 2 nitrogen atoms and 1 oxygen atom per molecule. So it asks us to show the resonance forms and to calculate all the formal charges in each of the resonance forms. Now, before you get started on this, I will help you out a little bit. So it's going to be helpful to know that sort of the skeleton of this molecule is going to have a nitrogen, and then the oxygen, like this. So 1 nitrogen is our central atom, and the other nitrogen and the oxygen are going to be the outside atoms. And another thing to kind of help you out here is the total number of resonance forms that you get for this should be 3 different resonance forms. So with that knowledge in hand, go ahead and pause the video, and I'll come back in a couple of seconds and start walking you through this. Okay, so hopefully you've tried this problem on your own. With any example, we need to know how many valence electrons we're dealing with. So each nitrogen has 5 valence electrons, and there are 2 of those, so 2 times 5. And then we need to add to that 6 electrons from our 1 oxygen. So 2 times 5 is 10, and 10 plus 6 is going to be 16 electrons. And I kind of already did step 2 for you. I showed you what the skeletal structure should be here. Notice that we have 2 bonds in the structure. So we used up 4 of our 16 electrons, meaning we have 12 remaining after we put the skeleton together. So the next step is going to be to assign these remaining electrons to outside atoms first to complete their octets. And the nitrogen on the left and the oxygen on the right both only have 2 electrons around them each right now. So we need to give them 6 more, so 3 lone pairs. And if we do that for 2 atoms, we'll exactly use up our remaining 12 electrons, so that's good. We won't have to assign any to the central atom. So we have a lone pair, 2 lone pairs, 3 lone pairs around the left nitrogen, and 3 lone pairs around our central oxygen. So this is what we have after step 3, and indeed after step 4 as well. Since there's no electrons left, we can't put any on our central nitrogen. Now we come to step 5, and this is where resonance shows up for pretty much any resonance example. Now, if we look at our central nitrogen right now, it's in a pretty bad state. It only has 2 pairs of electrons around it, 2 bonding pairs of electrons, one with another nitrogen and one with an oxygen. Now, that means it has 4 electrons, so to give it 8 electrons, we need to basically get 2 of those lone pairs that are on our outside atoms and come up with some resonance forms that use 2 of those lone pairs to fill out the octet of our nitrogen. And I said you have 3 choices here for 3 different resonance forms, and those 3 choices are: we could take both of those lone pairs from the nitrogen on the left-hand side, so that would leave us with 3 lone pairs minus 2 lone pairs, so just 1 lone pair, and both of those are bonds now, so we go from a single bond to a triple bond, and our oxygen is the same. Another option would be to take 1 lone pair from the nitrogen and another from the oxygen. So each of the outside atoms will have a double bond to our central nitrogen and 2 lone pairs. So we took 1 lone pair from each. And our third option is going to be to take both of the lone pairs from oxygen. So it's kind of like the mirror image of the first example that we looked at. So we'd have a single bond still between our 2 nitrogens, 3 lone pairs around that middle atom, or I'm sorry, around the atom on the left, and then we took a single bond and 3 lone pairs and turned it into a triple bond and 1 lone pair for this oxygen. So these are all different resonance forms, so we should probably put some arrows pointing in both directions between them. So this shows that these are 3 different resonance forms, and these are the final 3 resonance forms for these. Now, if we want to compare how well each of these things represents the true structure of nitrous oxide, N2O, what we can do is we can look at the formal charges on each atom and kind of compare and contrast them, see where our negative and positive formal charges end up and whether they're kind of idealized. So I'll go through in detail the calculations of the formal charges in the structure on the left-hand side. So I'll do the formal charge calculations for the left nitrogen in green, the central nitrogen in orange, and oxygen, I'll do that in purple. And if you go back a few slides, the formal charge for our green nitrogen should be the number of valence electrons in a neutral nitrogen atom, which is 5 minus 1/2 times the number of bonding electrons, so not the number of bonding pairs, but the number of bonding electrons. This nitrogen has a triple bond right here, so that's 6 bonding electrons. And then we're going to subtract the number of non-bonding electrons. Again, not pairs, but actual total number of electrons, which is 1 lone pair, so 2. And if you do this with the correct order of operations, we end up with a formal charge of 0 on our leftmost nitrogen. And remember, a formal charge of 0 is kind of the best case scenario. So if you have a resonance form where all of the formal charges are 0, that's probably a good indication that that's a good resonance form. Now let's look at the nitrogen here in the middle, which I'll do in orange. So we need the number of valence electrons in a neutral nitrogen atom, 5. We're going to subtract 1/2 times the number of bonding electrons. Now this nitrogen in the middle has 4 bonding pairs around it, so that's 8 bonding electrons. And subtract the number of non-bonding electrons. We don't have any lone pairs, so that's just 0. If you follow order of operations correctly here, we get 5 minus 4, which is positive 1. I'm going to indicate that as explicitly positive because positive versus negative is important here. So that's going to be positive 1. And then for our oxygen here on the right, we can calculate its formal charge as the number of electrons, valence electrons I should say, in a neutral oxygen, which is 6. Subtract 1/2 times the number of bonding electrons, so 1/2 times, we have just a single bond here, so the total number of electrons there is 2, minus the number of non-bonding electrons. 3 lone pairs gives us 6 electrons there. And if you do all that in your calculator, you should end up with -1. Now, one way to check your formal charge calculations is that all the formal charges on all the atoms should add up to whatever the charge is on your molecule or ion. So in this case, nitrous oxide, N2O, there's no charge indicated on that. So all the formal charges should add up to 0. And indeed, we have 0 plus positive 1 plus -1 gives us 0. So that's a good indication that we did the formal charge calculations correctly. Now, things to notice here is we have some formal charges that aren't 0. So on the central nitrogen, we're +1. On the oxygen, we're -1. That is not as good as if we were to somehow have all 0 formal charges, which none of these structures will. But if we have a negative formal charge and a positive formal charge, then the -1 should end up on the more electronegative atom. And oxygen, being to the right of nitrogen, is going to be more electronegative. So if we have to have a negative formal charge, it's probably good that it's on oxygen instead of nitrogen. Now, since I went through those calculations in detail, I'll just show you for the other examples what the formal charges should be for all the atoms. So in both examples, you're going to end up with +1 on the central nitrogen, because it always has 4 bonds and no lone pairs. For the nitrogen on the left, for the central one, it's going to be -1. And for this one on the right, it's actually going to be -2. And it's worth pointing out that formal charges are less ideal if they're non-zero, and the further away you get from 0, the worse they are. So a formal charge like +2 or -2 are usually signs that the resonance form is not that good. And then finally we can go through and calculate these for the oxygen. So here in the middle, that's going to end up being 0. And here on the right, when we have 3 bonds and 1 lone pair, which is not the normal state for oxygen, that's going to end up being +1. Now in all these situations, if you add up the formal charges, you get 0. So -1 plus +1 plus 0 is 0. And then on the right, -2 plus +1 plus +1 is also 0. Now, if we look at our central resonance form, right here, we can see that we have a +1 on the central nitrogen, so nothing has changed from the one on the left in that respect. but we took our negative formal charge and essentially shifted it from oxygen to nitrogen. So we shifted it to a less electronegative atom. So that resonance form in the middle is probably not as good as the first resonance form that we drew on the left. And if we look at the resonance form here on the right, this not only has all non-zero formal charges, which is bad, but we also have a positive formal charge on the most electronegative atom and a -2 formal charge on a less electronegative atom. So there's all kinds of indications here that this is probably not the best resonance form in terms of representing this molecule. So this form on the right is the worst representation, and this form on the left, where our negative formal charge ended up on oxygen, is going to be the best, and the one in the middle here is going to be intermediate between the two. So the true structure of nitrous oxide is going to be some combination, or really I should say some average of these three resonance forms, but that average is weighted more towards this thing here on the left-hand side, and less towards what you see there on the right. So those are your three resonance forms and how you can rank them for nitrous oxide. And that brings us to the end of the examples that I wanted to cover for Chapter 7. So I'll go ahead and stop the video here, and I will see you next time when we start with Chapter 8.